Hi everyone, so we'll be looking at the first topic, which is going to be the unit 2 in the IB chemistry guide. So we'll start with atomic structure, something that you're familiar with. And every unit will have a nature of science, what we'll call NOS. And the nature of science is going to set the context of that unit, but it can also be assessed. So you'll have to pay some attention to the NOS for each unit. So here, the NOS is about how our ideas, our understanding changes when instruments improve. So we'll start. Let's go through the history. So at the beginning, we had the Greeks, and they thought that the world is made of the 5 elements: earth, air, water, fire, and then there's space. The 5th element is debatable. There's different opinions of what is the 5th element. So I've mentioned only 4 here. And some Greek philosophers started to question the existence of particles. But this idea was rejected because there was no evidence of it. With time, and with the apparition of alchemy, where philosophers wanted to achieve eternal life or to convert substances to gold or silver, they started to experiment with things and to record evidence of what they were observing. So they were not processing any quantitative results. Quantitative means that has to do with numbers, measurements, but they were mostly observing things. And then they observed that when you burn things, it leaves out an ash that they called phlogiston. There is actually something called the Phlegin Theory, which was later on rejected. So Priestley discovered that you have different kinds of air. What does that mean? So Priestley found that if you take HCl, for example, reacting it with a metal, you get one kind of air that burns with a pop sound. And we know it's hydrogen. You take an acid, you react it with a carbonate, you get another kind of air that turns lime water milky, that we know is carbon dioxide. And you have, let's say, hydrogen peroxide in the presence of manganese peroxide decomposes to give another kind of air that relights a glowing splint. So Priestley discovered that there's different kinds of air, and he started to question the fact that air is not an element, because you can break it down into like different kinds of air. And it's when Lavoisier set up his very complex laboratory with more than 1,000 glassware, he started to measure substances. So he started to do quantitative analysis, and he measured the mass of substances before burning and after burning. And he actually defined an element as being something that cannot be broken down into any simpler substance. So for him, it was clear that air is not an element. He discontinued that idea, and he started to name substances. So he gave names to like hydrogen, oxygen, right? And then you have Dalton, who came in with his atomic model of matter. And it's only from his experimental data that he was able to say that matter consists of particles called atoms. And atoms, that means atoms. The name atoms comes from atomos, which means indivisible. And he did calculations to find the weight of atoms. And we're going to see how we do these calculations in our next topic. And found that an element consists of atoms of only one type, and that if you have more than one type of atoms, means that it's a compound, it's not an element. And he also found that atoms cannot be created or they cannot be destroyed, and he also started to list the names and the weight of the different elements. Then you have Mendeleev, who, as you know, created the periodic table based on the patterns of reactivity or properties of the elements. And then you have J.J. Thompson. J.J. Thompson, he proposed the plum pudding model for the atom, where he said that you have the charge, the positive charge, which is spread throughout the atom, and then you have the negative charges that are dispersed in the atom.
It was here in Cambridge that the first clear evidence for smaller objects inside the atom was found. Many of the great scientists of history have walked these streets, and one of the greatest was J.J. Thompson, who became the director of the old Cavendish laboratory. In 1896, Thompson had just got his hands on this new piece of kit. Now, it's essentially a particle accelerator. When this plate's heated, particles are emitted. They're accelerated by these electrodes. They pass through these two plates, across which you can apply a voltage, and they hit the end of the bulb here on a screen which glows so you can see the beam. Now, this is a modern version of Thomson's apparatus. Again, we've got the particle accelerator, and there's a screen in there so you can see the beam glow. What Thompson did was he varied the voltage across the plates, and he measured the amount of bending as the voltage changed. That allows you to deduce the mass of the particles in the beams. Now, the lightest known particle in Thomson's day was the hydrogen atom, but Thompson found from these measurements that the particles in this beam are almost 2,000 times lighter than hydrogen atoms. Thompson had discovered the first subatomic particle, the electron.
The electron owes its practical utility to its smallness. It might the parody Shakespeare say, "My use is great because I am so small."
The electron was the first discovery of a fundamental particle, and it is interesting to realise that more than 100 years later, the electron is still, to the best measurements we can do today, a fundamental letter of nature's alphabet.
We can use electrons as ways to probe materials and look at the structure in electron microscopes or in big machines like this accelerator behind me. Pretty much all of everything we do in the 21st century depends on understanding the properties of electrons.
Thompson had discovered that the atom is not the fundamental building block of matter. There are smaller objects inside. So atoms could no longer be thought of as hard, indivisible spheres. But how did the electrons fit inside the atom? Thompson suggested that the atom was something like this muffin, with the negatively charged electrons embedded in a positive body. It would be a student of Thompson's that proved him wrong.